Lesson 3.1, Exponential and Logistic Functions. In this lesson, when we're talking about these types of functions, we're going to be working with more real-life situations and story problems. The definition of an exponential function, we've talked about this in the past. Let a and b be real number constants. An exponential function in x is a function that can be written in the form f of x equals a times b raised to the x. We know it's an exponential function if our variable is in the exponent. A couple of the key parts: a is referring to the initial value and b is the base. Also with b, that is always going to be a positive value. The way we distinguish an exponential growth function from an exponential decay function, we're looking at that value of b. If b is greater than 1, it's exponential growth. If b is between 0 and 1, then it's exponential decay. It can never be equal to 1 because if b was equal to 1, well, 1 to the x would always be a value of 1, so then we would actually have a horizontal line and this would not be an exponential function. First example problem: suppose you put $1,500 into a savings account that earns 2.25% interest. How much money will you have in the account after 5 years? We have to use a form of an exponential equation. This is for compound interest. A equals P times 1 plus R raised to the T. P stands for the principal amount or the initial amount. R is referring to our rate. We have to take that percentage, convert it to a decimal when we plug it into this formula. And then T is referring to time. It's always going to be in years unless we specify otherwise. Something to be aware of with this form of the function: that value we have inside parentheses, 1 plus r, that is the same as the b value we were looking for in our general form when we had y equals a times b raised to the x. This is the same thing as b. So if this value turns out to be greater than 1, we know it's going to be exponential growth. If this value is between 0 and 1, it's going to be exponential decay. So back to our problem, we want to determine how much money would be in the account. So we're looking for that amount A, which is going to be equal to P is our principal amount, how much we're starting with, which in this case was $1,500. Taking that times 1 plus, we have to convert our interest rate to a decimal. So to convert a percent to a decimal, move that decimal place 2 spots. So this is 0.0225. And now that's raised to not the t power. We know t is 5 in this case. Now you would just plug this in a calculator and round to 2 decimal places since we're talking about money. So in 5 years, that account would have $1,676.52. That makes sense. Our value is larger, as it should be. Our b value was greater than 1, so this would be exponential growth. It's increasing. Example 2. Suppose you get a new car that costs $14,500. If the car depreciates by 12% each year, how much will it be worth in 4 years? Depreciate, think decrease. That's how much the value of the car is going down each year. So we're still going to have that same type of equation last time. Instead of A, I'm going to use V, standing for or representing the value of the car at a given time after so many years. So V is equal to, we want to write the original amount. We got the car for $14,500. Now we're going to take that and multiply it by 1. And this is going to be minus now. Depreciate, we're decreasing, so we have to take 12%, change that to decimal form, move the decimal place twice, so minus 0.12, and then raise that to our exponent of 4 because we're looking for the value of the car after 4 years. Again, we know this is exponential decay because we're decreasing. If we look at our b value, 1 minus 0.12, this value is between 0 and 1. Now we would just plug this in your calculators, again rounding to 2 decimal places because this is dealing with money. So our answer is going to be approximately $8,695.58. So if you bought a car for $14,500 in 4 years, if it depreciated by 12% each year, the car would have a value of $8,695.58. The last function we are going to discuss in this lesson is the logistic growth function. We use this function when talking about populations. For instance, if we were talking about the number of deer in Davidson County, Game, Fish, and Parks could use this type of equation to model and predict what they think the population will be in the course of 5 years. The value of C, which is in the numerator, that tells us the maximum value that a certain area can sustain. So the population can never be greater than this value. A and K are some positive constants that we use within our function, representing different criteria. We have E, which is that exponential constant, 2.71. And then we have our variable x in our exponent. This isn't an exponential function, but that's why it's very similar to one, because that variable occurs in our exponent. The last example we're going to discuss, this is going to be similar to example 8 in your books, so if you want to look at another example to go through this again, you can look at example 8. Using 20th century U.S. Census data, the population of Ohio can be modeled by the following function. P of t equals 12.79 divided by 1 plus 2.402 times e raised to the negative 0.0309x. P is the population in millions, and x is the number of years since April of 1900. Based on this model, when was the population of Ohio 10 million? Technically, we could solve this algebraically. It becomes a lot more difficult to solve this algebraically, but it is possible, and that's something we can go through in class. All we have to do is, since we're looking for when the population was 10 million, when the population, or x, is what we're trying to solve for, the number of years since 1900 when the population was 10 million. So we would set our equation equal to 10 million. The easiest thing to do in this case is to graph it, which you can see here towards the bottom right. We have the graph of the logistic function, which you can see has a slight curve to it. And then we have our 10 million. So this represents the 10 million, the population we're looking for, how many years it took to get to that. And then this is the logistic function, the part on the right side of the equation. So if we graph those two, we're looking for when those two graphs intersect, which you can see is approximately 69.67 years since 1900. So you could just round that to approximately 1970. Okay, you could round that 69.6 up to 1970. Or if you wanted to be a little more specific, you could go 1969, and then 0.67 is approximately 2/3, so that would be 8 months. So this would be 69 years and approximately 8 months. So in 1969, 8 months into that year, the population of Ohio would be approximately 10 million. To end this lesson, we'll review a little history, talking about that natural base, that natural number E. It's named after Leonard Euler. Okay, the concepts he discovered when talking about that value of E, that's really important when we start talking about calculus applications. So those of you that take calculus will deal a lot with exponential functions. And then we have this little phrase that we've discussed in the past to help you remember the decimal approximation for that number E.